Determining celestial distances is one of the most important things that astronomers can do. There's a good side and a bad side to that. The bad side is that it's somewhat difficult. It's not like we can just take a ruler here on the surface of the Earth in our office, put it up against a pen or some other object, and determine how big that pen is, how long that pen is. Can't do that in outer space. We have to use other types of rulers. The good news is there are a lot of different types of those rulers. And what you see here is the most basic type, and that is parallax. Parallax is similar to what you have noticed if you close one eye. So right now I've closed my left eye. I'm holding my thumb close to me. I'm looking at it with my right eye. When I close my right eye and open my left eye, my thumb shifts with respect to the camera, which is off in the distance. For a farther away thumb, that shift is even less. So there's a relationship between the shift here, which is called the parallax angle, and how far away this star is. Unfortunately, that only works for the nearest stars. It's very precise. It's the most precise method, but it works only for the nearest stars. When we launched the Hipparcos satellite and we started taking measurements above the Earth's atmosphere, that really helped because the atmosphere tends to fuzz out teensy tiny changes in position in the nighttime sky. To notice things a little bit farther, we use something called a Cepheid variable. Cepheid variables have been known for a few hundred years. They are variable stars. The first one was in the constellation Cepheus, thus the name Cepheid variable. And its brightness varies in a very periodic way. So look at how this shape here of the graph is the same day after day, week after week, month after month. So for this one, the brightness peaks every 50 days. In the early 1900s, Henrietta Swan Leavitt, who was one of the Harvard computers, one of the female astronomers at Harvard, she noticed there was a relationship, looking at close-up Cepheid variables, that we could actually determine their distances using other methods such as parallax. She noticed there was a relationship between the luminosity of the Cepheid variable and its brightness shift. It's the period of its brightness change. So the shorter the period, so the less time between maxima, so as the peak-to-peak distance gets smaller, or for peak-to-peak distances that are smaller, the luminosity is less. So if you know the luminosity of it, what it actually is, and you know the luminosity that you can measure from here on Earth, you can determine the distance. And this is what's known as a standard candle, because there's something standard about it that's independent of distance. If you observe a Cepheid variable and you can measure its periodicity, you know its luminosity, and you can figure out its distance. But again, Cepheid variables are single stars. They don't work for objects that are super duper far away. The next type of standard candle is a white dwarf supernova. A white dwarf itself is not very bright, but a supernova is. So a white dwarf supernova, let me move my cursor out because that kind of looks like a supernova there. A white dwarf supernova is in a binary star pair, white dwarf and probably a giant, almost certainly a giant star, such as a red giant. The white dwarf pulls mass from the red giant. When it pulls enough mass such that it gets to be greater than 1.4 solar masses, the white dwarf cannot sustain itself as a white dwarf, and it goes supernova. Because all types of white dwarf, or all white dwarf supernova, come from the exact same type of star and the exact same mass, plus or minus a pretty small percentage, they're going to have the same luminosity. So again, here's something where we know what the luminosity is because it's a white dwarf supernova. We can measure its actual luminosity. We can measure its luminosity here on Earth. If we know the actual luminosity and the measured luminosity, we can determine the distance. It's kind of like with a light bulb. If you've got a 100-watt light bulb, you know what the intensity of that bulb is. If someone moves that 100-watt light bulb far away from you to some distance that they don't tell you, but then you measure the intensity of the bulb at whatever that mystery distance is, because you know it's a 100-watt bulb, you know its luminosity, its standard luminosity. You can measure its luminosity when it's 50 meters, 100 meters away or whatever. Using those two numbers, you can figure out its distance. That's how the standard candles work. But even white dwarf supernova, those are single stars. Even though they're undergoing a catastrophic life-changing event for the star, they're still single stars. Hubble noticed that in distant galaxies, he could use star clusters that orbit those galaxies as standard candles, because star clusters, globular clusters, formed at about the same time, so they have a predicted luminosity. And because Hubble or anybody could measure the luminosity as viewed from Earth, again, you know the actual luminosity, you know the predicted luminosity, you can determine the distance. Although in this case, he used a little bit more, it was a little bit more subtle than just the brightness of the bulb, so to speak. He looked at the distribution of the light, or the spectra. And that spectra then was shifted, redshifted, because that object was moving away from us. So if that cluster should have, a globular cluster should have kind of a standard spectra that looks like this, but instead it looks like this, you notice it's been shifted over. That redshift says that the galaxy is moving away from us. Hubble studied a bunch of these, plotted them out, and noticed that there's a relationship between the recession velocity, which was determined by the redshift, and how far away it is. So the solid red line is the best prediction, and then the dotted red lines are the range of predictions. Notice down here for lesser distances, there is no dotted red line. The model and the measurements work pretty well. But as you're measuring things that are farther away, there's a little bit more variability in your measurement. But sort of the standard here is the slope of the line. Notice it's a straight line. And the slope of a straight line here is represented by rise over run. So the rise here, the units are kilometers per second. So something's receding at a certain number of kilometers per second. The x-axis, or the run, is the distance in millions of light years. So the slope here is 22 kilometers per second per million light years. So every additional million light years a galaxy is away, it's moving away from us at an additional 22 kilometers per second. So a galaxy that's 100 million light years away is moving 22 times 100, or 2200 kilometers, 2200 kilometers per second per million light years. And then if we double that distance, we're going to double that recession velocity. So the slope of it is, the slope of the line is the same. And this was one of the biggest clues here to the expansion of the universe. So that summarizes most of the ways of determining distances. I didn't mention radar. Within our solar system, we can actually shine a radar beam off of an object. So we've done that for the moon, for Mercury, for Venus. More distant objects, the radar beam spreads out too much and not enough of it reflects back to us. Then we can use parallax. We can use something I didn't mention called main sequence fitting. That's another type of standard candle, essentially, using nearby clusters. And then I mentioned these other three. So the variety of methods allows us to determine a variety of distances. So I mentioned universe expansion. That's making me hungry. I want some raisin bread. So why is it that more distant objects seem to be moving away quicker? Are they somehow in actuality moving away quicker? Is there something physically out there that's pushing them away quicker at a greater rate? No, think of raisin bread. So you make the raisin bread, it's just the dough, you put it in the oven, and of course it expands. Before you put the bread in the oven, before there's a bun in the oven, you have raisins that are a centimeter apart. But those expand, they expand, so after they've expanded, let's say they're 3 centimeters apart. But from the point of view of the so-called local raisin, these raisins have moved farther away. So the first raisin, it was 1 centimeter away, now it's 3 centimeters away. So if there's a standard baking time, that thing has moved a certain number of centimeters per hour after 1 hour of baking, because it's moved 2 centimeters. The next raisin has moved 6 centimeters away. It used to be 2, now it's 6, so it's moved 4 centimeters in that hour. The last one used to be 3, now it's 9. 9 minus 3 is 6, so it's moved 6 centimeters in that hour. So the more distant raisins seem to be moving away from the local raisin quicker. That's because all of space is expanding. Raisin number 3 isn't moving any quicker from our outside the universe point of view, our God point of view, so to speak, but it is as viewed from the local raisin. Another analogy is an expanding balloon. So take a balloon that you haven't blown up yet, take a Sharpie, and then put some equally spaced marks on it, and then blow up the balloon. You'll notice that all the spots move away from each other in the same pattern. The distance between A and B used to be a certain distance. Now it's changed. The distance between A and D was a certain distance. Now it's increased, but the distance between A and D has increased by more than the difference between A and B, similar to the raisin bread. And this isn't just galaxies moving farther apart through space. This is actually space itself moving. So in this analogy, the balloon is space itself, more precisely space-time, and the black dots are galaxies. So the black dots aren't moving on the surface of the balloon. It's the balloon, space-time itself, that's expanding. So anything within that space-time is expanding, including light. So as the universe expands, those light waves expand as well. This light wave has a longer wavelength than this one, so it has redshifted. It's shifted towards the longer wavelength end of the spectrum. And the color here that they show you hinting towards red reminds you of that. That doesn't mean that all light from distant galaxies is red. That just means that the wavelengths have been stretched out, and stretching out for the visible spectrum, the short end is the blue, the stretched out long end is the red end of the spectrum. So that is a little bit on distances and the expansion of the universe.